Ah, hello everyone. Hello. Welcome to my classroom. Ho ho. Ho ho. I hope you're all prepared because we're about to dig into some very deep and complex subjects. And oh look, I got new BGM. Whoa. Yeah, that's nice. Boo! What? Oh yes, Skylar. I'm going to teach you the best of the best of maths. I've taken up to like, I think I've taken a lot of math and I really like math, so hopefully we'll do good. Oh look, the chat's working. That's new. Huh. Oh well, I'll just keep that there. But yes, we're gonna be doing a lot of maths today. I'm pretty good at it and I understand it a lot, so I hope I could teach you to the best of my abilities. You heart limits? Well, yes, I do too, because that's what we're gonna be learning today. We're only gonna be covering limits if I don't know, if I feel like it in the future. I'll cover like derivatives, integrals, that type of jazz. Ooh, let me move the chat because it's not fitting on the screen. Calculator. Is this one or this one? This one isn't working. All right, let's keep that up there. All right, so yeah, we're only gonna be doing limits, derivative. Well, not derivatives this stream. Maybe another stream. Limits, but I kind of bombed when it came to that, when I've done that, so we're not doing that. When's the Roblox Squid Game video coming out? I want to have it out before Squid Game season, the new Squid Game season comes out. I have to push out another video first and then it'll come out. Yes. I have 2 videos that I want to push out before the Squid Game video. So before that. Yes, so that's when it's gonna come out. So hopefully in about less than a month. Yes, but anyhow, let's dive right into my favorite subject, math. Anyhow, I prepared like the best. I spent like the whole day doing this, by the way. I'm a little rusty too, so I had to like practice myself. But don't worry guys, because I'm pretty cracked at this. Specifically limits and derivatives. Integrals, I'm really rusty on integrals, but I could do it. I could do it. I just need a little bit of practice, but I'll be fine. And y'all be fine too, because when y'all take calc, or if you're already taking calc, this is a refresher. But if you haven't and you're gonna take it in the future, man, you're gonna ace that test, because you see I'm a certified professor. So yeah, today we're gonna be covering calculus, limits, and continuity. I of course am Professor DJ. Just look at my professor glasses, right? You don't see a professor with the glasses such as these. It means I'm smart, you know? Yeah. Yes sir. And ooh, wait, where's my? I wonder if I could just. Oh yeah, I can. Ooh, that makes things easier. Oh yes. So just to get right into it, what is a limit? Now, for all of those who have taken algebra, a limit is essentially, well, no. Let me explain it. So, in algebra, they teach you what is called the average rate of change. A limit essentially goes more into depth in regards to slope and starts evaluating something known as the instantaneous rate of change. So, the rate of change at an instant. Now, the limit is actually something, it's not really defining the instantaneous rate of change, but it's more so describing the behavior at a specific point, right? Or what I wrote down here, it describes the behavior of a function as the x coordinates on a graph approach a specific value. And they could be used, as I previously stated, to either find the instant rates of change, prove continuity, which we will be discussing later on throughout this whole lesson. Lesson. And they are used, well, I already said it, but they're used to describe end behavior. They're denoted as this, you know, right here. This is. Oh, oops. Wait. Oh no. Did I click the wrong thing? No. Oh, look, I have a little laser pointer. They're denoted as such right here. So when I'm saying that x is approaching a certain value, as we can see of this function right here, this is f of x. Let's say this is f of x. As x approaches from the right, this is c right here. As x approaches from the right, the y value is going to be f of c, right? And this is the left actually. Yeah, this is the left. My bad. Ignore what I just said. As x approaches from the left, all the x values on the left side, right, are approaching this y value when the x is c. On the right side, the same thing is said. It can be said because look, all the right x values are approaching this y value when x is c. See, as f of c. So that's essentially what a limit describes. It describes the point that all the x values are approaching when you're choosing a specific x value. It's a little complicated, not really, but you know, with practice, it makes a little more sense. Maybe my wording isn't the best, but it's pretty self-explanatory. Look, all the x's approaches a specific value. All right, that's pretty much it. They approach a specific value if the function obviously exists. All right, so let's move on to the next slide. Oh, can I? Yeah. So where graphs where limits do not exist. So there are cases, of course, where limits exist and limits don't exist. This is one of which in which, of course, it doesn't. So let's evaluate this graph. We have a graph. I don't know. This is probably like a piecewise function of sorts or something like that. There's an asymptote, a horizontal asymptote over here. I believe it's at like y. Is it? Yeah, it's y equals 0. Yeah, y equals 0, something like that. But anyhow, like I was previously saying, limits only exist if both the left-hand sides of the left-hand x's and the right-hand x's approach the same y value. In this case scenario, if we evaluate the limit as x approaches, what is this, 0? Yeah, as x approaches 0, we find that the left side is all approaching -1, and all of the right side is only approaching +1. Now, obviously, this is not the same y value, and this is a big problem, because that means that the limit does not exist. Whoa. And that's pretty much most of what's going to happen in regards to limits. We're going to evaluate whether they exist or whether they don't exist, whether they're approaching a same y value or whether they're not approaching the same y value. And that's I'm going to be completely honest, that's like at least 2/3 of calculus. Not really, because there's other parts of calculus, but if you really look into it, calculus is just limits redefined in different ways. Derivatives are a form of limits. Integrals are a form of limits. The Riemann sums are a form of limits, but there's a lot of other things. You could apply limits to a lot of things in life, but I don't know. They just comes in many ways, shapes, and forms. But in terms of math, limits are strong, bro. Trust me, they're strong. But like I was saying, right here in this case scenario, they do not exist. The left-hand side and the right-hand side do not match. They don't exist. Oh, one thing to note though. Okay, so let's say there was a straight line right here, right? But at this point, I could actually draw that. Let me draw that instead of just yapping about it, bruh. Okay, so I gotta. All right, so let's say, oh, oops, yeah, let's just keep it red. Ah, fuck it. Okay, so let's say this was the original graph, right here, but there was a hole. Let's say this is, what is this? Y equals 1. Y does not equal 1. It doesn't exist. Okay, let's say this doesn't exist. Even though this value doesn't exist on the graph, the limit might still exist. Well, it does exist because both the left-hand side and the right-hand side are approaching the same value. So, and because of that, the limit does exist. All right. So just because a graph has a hole in it, it doesn't mean that the limit doesn't exist. It could very well exist. You just have to look at both the left-hand side and the right-hand side. Know your left and right, and then you'll be fine, and you'll pass that test, at least the limit portion. And yeah, moving on. Oof. I hope I'm doing a decent job. I'm not gonna lie. I don't know if I'm doing a great job, guys. This is my first time teaching. I am a great professor and all, but I don't know. Shit. Am I really? Oh wait. Hold on. Just give me 1 second before we continue. I gotta check if. Oh, 1 second. 1 second, class. 1 second. Wait. Oh, there we go. Bruh. Where is it? Where is it? There we go. I'm just doing a little thingy-mabob real quick that I have to fix. But we'll be right back into the limits. Don't worry, guys. I'll keep educating y'all. I'm a great professor. Oh, what the heck? I have an ad? Bruh. Why'd I get an ad? I got an ad. I have Spotify Premium. Why am I getting ads? But what the heck? What is this? Okay, whatever. I guess no more music. Fuck that. I'm not doing that. That's really weird. I'm not gonna lie. How I shouldn't be having that. All one of your current viewers already know this. All one of your current viewers already know this, but I feel like I didn't would. If I didn't, I wouldn't be learning. Oh, okay. What? All right, now let's go back. Bro, I can't change my pen. Okay, this isn't even the right color. There we go. I wanted my pen to be white. Okay, now we can continue. All right, so let's go back to. It's not letting me. All right. Why are you not letting me? Bro, it's ruining my slideshow. Ah. Okay, there we go. So these are other examples of where limits don't exist. So this is a case in which a function is oscillating. Essentially it's approaching, both sides are approaching a value, or they look like they're approaching a value. They're going in a specific direction. But since they're both moving in this like weird zigzag curve, they're not ever gonna approach a finite value, meaning that the limit doesn't exist. A little tricky, not gonna lie, but hey, it is what it is, all right? It is what it is. So yes, this is a case in which a function is oscillating, and when they oscillate, the limit doesn't exist. Funny thing though, I don't know, I don't remember. I'll have to fact check this. I'm pretty no, they don't. Okay, never mind. I'll just keep my mouth shut just in case. I don't want to trip y'all up because of my goofy little brain. Oh, finally, a solving example. Okay, so this is how I'm gonna show y'all how you evaluate a limit. Right? Because you see, well, obviously, like every other math problem, you don't only just use graphs. What are you? Who do we think we are? We make our lives hard. We don't just look at graphs to evaluate limits. No, we actually do math. And there's easy ways to do it, and there's hard ways to do it. And we are only gonna be doing somewhat hard examples. I don't want to do something too complex, so I chose like mid-level examples. Anywho, right here, we have the limit as x squared of, as x approaches 0 of x squared minus 2. Right? Now, how exactly would we evaluate this? Well, it's simple. The method is to simply plug in 0 into all instances of x, or whatever x value your limit is approaching. You have to substitute it for x. And that's pretty much how you solve most limits, unless you get a very weird situation in which it is undefined. And I'll show you all an example of that later. But right here, we just simply do this. So so this is the limit as x approaches 0 of, well, we don't really have to write the f of whatever. I don't think that's necessary, but I just did because it's a bad habit of mine. But you don't usually get that in problems. So you just usually get this. Sometimes not even with the brackets, but whatever. I like to use brackets because it makes things more clear. So yeah, you get that. You substitute when you substitute value into the limit, you get rid of the limit notation. So you're just left with that. And then you simply just evaluate that. It's basic arithmetic. So 0 squared minus 2 equals minus 2. And so then that's pretty much the solution. But then you have to write it in the proper notation. So you go limit as x approaches 0 of x squared minus 2 equals 0. Equals, oh, fuck, minus 2. And that right here is your, that's your answer. Pretty simple stuff, but of course it gets harder. And we're about to look at that. Oh man, what? I hate how this game, why is it doing this? No, oh my god, wait. All right, I don't like how my PowerPoint's goofing up right now. Oh, there we go. Ooh, this one is a tricky one. Okay, so remember how I was saying that there's cases in which you get a instance in which the limit doesn't exist? Well, this is one of them. So well, it's not that it doesn't exist. It's undefined. All right. And by definition, an undefined function doesn't exist. Well, the limit doesn't exist. An undefined function could exist. Wait, what? No. Okay, whatever. I'm tripping myself out. Okay, let's actually get into this. So, right here, there's a problem. If we use the substitution method, we're gonna get a 0 in the denominator, and we can't have that because that is a no-no in math. No. That is a big law. It's a law-breaking thing. You can't divide anything by 0. So, we gotta do something about that. And what do we do, you may ask me? Well, it's simple. I, being the best professor out there, know that we must factor. Whoa, factor. We must factor. We have to factor a lot. We either have to factor or use some other weird algebraic manipulations in order to solve limits. So, in this case, we could do a lot of things, right? We could use the differences of cubes formula, which, be pretty easy, I guess. Or we could do something a little easier that some of you might know, some of you might not know. I don't know. We could just do division of polynomials, or synthetic division, whatever works for y'all. I like to do long division, so that's what we're gonna do right here. Remember, the rules of long division. It has to be in this form: x minus something or x plus something. Can't be in the degree has to be 1 of the whole entire term when you're dividing. So this is x cubed minus 1. X cubed. Now, a fun fact, I had a quiz on this one time, and my goofy ass forgot how to divide polynomials. But guess what? After years and years, I finally remembered how to do. I'm kidding. It's not years. I literally looked it up like a few days afterwards, and I was like, oh shoot, I forgot how to do it, even though I used to be a pro at doing it. But oh well. Nonetheless, I'll show y'all how to actually do it. Hopefully y'all could learn from my mistakes. So whenever you don't have terms that are, you know, descending, yep. So you always need an x cubed. Well, yeah. So since it's an x cubed, right? We need more terms. We need an x squared, an x, and whatever the fuck the minus 1 is doing here. We just have to add them. I don't know why, you just do. All right. So right here we're gonna have an x squared plus an x. Now, a important thing: the coefficient is gonna be 0. just keep that in mind. All right. Think of this as just a placeholder term, but you need it to divide and actually complete the operation. But of course we're gonna add the 1 right here. So yes, we're gonna be dividing. So now it's just simple division, okay? So what two numbers? Well, not what two numbers. What number multiplied by x gives you x cubed? Well, simple. That's x squared. X, right? Right. It's pretty simple. So x squared. Oh, but then you have to multiply the minus 1. So then you get minus x squared. Right? These two cancel out. You get 0 x squared minus x squared. Remember, this thing is worth 0. So it's a placeholder. It's not actually, it doesn't really hold a value. So this is just gonna go down. Oh wait, my bad. I forgot to distribute the negative over here. Silly mistake. Yeah, so this just goes down as positive x squared. Over here, we gotta do this whole thingamabobby thing about again. Look. So what do we do? Well, we have a positive x squared to get an x, and well, a positive x squared. So we need to multiply something to get x squared. What do we do? Simple. We just multiply by x. A positive x too because of the positive sign. You know, inverse. Anyhow. Ooh, well, I gotta move this over here, so I'm running out of space over here. So we get plus x. So plus x squared minus x squared. And then we have to drag down the 1 over here. Minus 1. We drag down this 1 because it's just right there. Then we get this. What? Oh, my bad. It's the x. We drag down the x. Sorry, guys. X. Wait, what am I doing? Hold up. Okay, I just goofed myself up. I tripped myself up because I had to move it over here. Yeah, so we subtract the x squares. This over here, we multiply x by x. This minus x. But this is 0, so this goes, you know, plus x, I mean. Yeah, so that's plus x. Yeah, alright, yeah, that adds up. X minus 1. And, so you get x minus 1 at the end. If you didn't goof up my math because I moved stuff over. No, I'm just a pro at this. But anyhow, simple. Now we see that we have the same terms on both sides. So what do? Simple. Multiply by 1. Woo! We multiply by 1. So this would be, well, your answer in terms of the division. But then you have to actually evaluate the limit. So just give me a second. I need to erase some stuff. So the answer is x squared plus x plus 1. So now we're just going to be evaluating this. Yay, and that should be, well, at least it should be easier. What is it? I don't know. Yeah, it really is. I'm not gonna lie. You're not gonna have any discrepancies. I mean, look, you're not gonna be dividing by 0 anymore, which is an indeterminate form. And you're actually allowed to evaluate the limit this time. So the limit as x approaches 1. What is that? Simple. We plug it in. So 1 squared plus 1 plus 1. 1 squared plus 1 plus 1 equals 3. So at the end of the day, right, the limit as x approaches 1 of x squared plus x plus 1 equals 3. Well, I mean, not this one, my bad. This isn't the right. It's supposed to be this. So just imagine I put that there. I goofed up. Yeah, imagine I plugged x minus 3 over x minus 1 in here. And then we'll be fine. Okay. So yeah, that's a little bit one of the trickier ones, but that's what you're supposed to get. Now, if anyone wants, y'all could fact check me on it because I sometimes goof up. But that's how it should be, unless I goofed up. Which y'all feel free to fact check me if you want. I don't know, ChatGPT it or something. Photo math. I don't know. But yes. Anyhow, now that we did that example, I think we have another one coming up. Final one on. I think it's only like 1 to 3 examples that I prepared for like each topic. We have a lot of topics to go over. I'm going over like the whole like module on limits because I care about my students. Oh, this is an easy one. So this, like, we did the differences of cubes, but this is an example on the differences of squares. Yes, differences of squares. So hopefully y'all are familiar with the differences of squares. If y'all aren't, then I'll teach y'all. I'm about to teach you. Okay, so long story short, right. Long story short, when you have a negative sign of something squared, you are able to gather 2 factors out of it. Only, yeah, only if you have a minus in the middle, and the fact both factors are some type of like unit squared. So like right here, should it be as x approaches 2? As x approaches minus, oh, no, we're not doing that for this one. Oh yes, you're right. You're right. No, no, no. You are right. We're gonna be doing -2 for this one. You are right, Skylar. Oh hey, Molten. I also want. Nah, I'm kidding. This one should be as x approaches -2. You're right. Yeah, because I want to do indeterminate forms, because those are harder. Wait, hold up. No, yes, I'm right. I was tripping a little. Okay, yeah, yeah. So like I said, difference of squares. Difference of squares. So let's evaluate it then. So we take the limit as x approaches -2. Because we don't want to do 2. 2 is too easy. I mean, we could do both. Screw it. Let's do both. Just to see what happens. It's gonna be easier. Let's do the easy one first. Then we plug in. So it's gonna be 2 squared minus 2 over 2 plus 2, which is equal to 4 minus 2, 2 over 8. And then we always have to simplify. So that's 1/4. So limit as whatever the limit as x approaches 2 of x squared minus 2 over x plus 2 equals 1/4. So that's the easy one. We don't really have to do anything. But now we're gonna do the harder one. So let's just hold. Give me a second. Yeah, let's do the harder one. That was the easy one. It would be 2/4, not 2/8. Well, I'm bad at doing math. No, I'm kidding. I'm bad at doing like mental math. All right, don't. All right. What do you mean? Wait, 2/4. Oh yeah, you're right. My bad. My bad. Yeah, cause I'm not really that great at addition, guys. I could do the hard stuff. I can't do the basic addition stuff. All right. It's a little bit of a flaw I have, but I could do it. I could do it. Sometimes my eyes play tricks on me. You see, that's why I have the little glasses on. But you're right. Thanks for calling me out. Anyhow, hopefully we don't mess up for this one though. We're gonna be doing limit as x approaches -2 of x squared minus 2 over x plus 2. Obviously, we're gonna have an indeterminate form on the bottom because we get a 0. Show that right here. -2 plus 2 over 4 minus 2 equals 0 over 2, and that's just that no. That's a no. That's a no. So what do we have to do? Well, simple. Like I said before, differences of squares. All right. So that's x plus 2 times x minus 2. Hey, that's this comes from that. This thing right here, it comes from that. Wait, no, this thing right here comes from this thing right here. All right, just to avoid confusion. And then we get x plus 2. Now, oh yes, we have to imagine I drop this limit notation down. Some people take some teachers like to take points off just because you don't bring the limit sign down. I mean, I don't really care. You're doing the same thing anyways. You're gonna get the same answer. But some people think it's wrong. So if you're gonna actually do this for an assignment or something, I'd suggest doing it, keeping the limit sign all the way up until you plug stuff in. So yeah, do that. Anyhow, like I was saying, we have two terms over here that are literally the same, and you know, they're being divided by each other. So we could easily cancel these out, and we're left with this x minus 2. So now we're only going to be evaluating the limit as x approaches -2 of x minus 2. X plus 2 times x minus 2 equals x squared minus 4. Huh? Oh yes, that would be if you distributed. But we don't like distributing over here when we're evaluating limits. No. If you were to do that, you would still get a 0 in the denominator. So what you're trying to do when you're evaluating limits and there's an indeterminate form is trying to cancel out something from the numerator with the denominator, so you could just get like something more, I don't know, something easier if it's possible. So that's why right here we just cancel it out. We cancel it out. We got x minus 2, and when we evaluate it, we get minus 4 because we plug in -2 into x, get -4. This is with the factoring. Yes, yeah, I know. If you were to distribute this, then yeah, that's what you would get. We're not meant to distribute though. We're not trying to do that. We're just trying to cancel it out. Oh yeah, but yeah, we pretty much solved this one. So this is the limit right here. As limit as x squared, limit as x approaches I forgot that again. As x approaches -2 of x squared minus 2 over x plus 2 was minus 4. So yeah, that's limits, as or at least how to like input them. I'm not sure if I prepared another one. I'm pretty sure I didn't. Nope, I didn't. No, it's just the same problem. Oh, okay. Now we're gonna get into like one of my favorite subjects, the derivative. Not the well, it is a derivative, but let's just pretend that we don't know about it. If you do know about it, it's like it's sacrilegious to know about it. All right, hush, 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 hush. So we're instantaneous rate of change. It's related to limits. It's really important too. So and out, like I said before, I think at like the beginning of the stream, Algebra 1 introduces the average rates, but instant rates are the key to more realistic practices and approaches within like calculations, and more specifically like engineering applications and that type of jazz. You know, y'all wouldn't want like it's some guy to approximate how to build a bridge, would you? Because then it would just fall. I don't think that's good. So that's why we use more exact calculations, and that's where like instant rate of change comes into play. Also for like speed and that type of jazz, you know? So this is what we use instant rate of change for. Now you could do this in two different ways. For an approximation, we use obviously the average rate of change formula. Right here it's notated in a different way, but it's really just, oh wait, it's just y2 minus y1 over x2 minus x1. It's the same thing, it's just notated in a different way. So same thing. This is just used to make an approximation of this thingy. Ooh, and now that we know about limits, we could actually do this thingy. So yeah, this is the exact definition of what instant rates of change are. They just give the slope of a specific point, and that's pretty much it. Now if I were to go into depth about it, they don't really give the point of an exact the slope of an exact point. They give the slope of a line tangent to that point, and you know, by association, that point has that slope. All right. So that's where you get that from. So this right here gives you the slope of a line tangent to this point, which shares the same slope. Hopefully that makes sense. If not, I'll just show y'all with proofs or whatever. Anyhow, let's just move on to it. Hopefully y'all get it. Y'all get the idea. You'll get the idea soon. Okay, so here's an example. I think I only prepped like one question for this because it's, I don't know, it's pretty tedious, but it's not that hard. At least I don't think so. So let's say we're giving the function f of x, right? F of x, yeah. which in this case is x minus 1 squared. And the point 2, comma 4 is given. We have to find the line tangent to the given point. Now, this problem involves, I believe, yeah, this problem involves like 2 steps. First, we have to actually evaluate, we have to find the instant slope of the function at the given point. And then we have to use a formula to actually develop the line of the tangent. The line tangent to the point. Okay. That's a little bit of a lot. But it's doable. So, I don't know if y'all recall, because it was a pretty fast glimpse. Oh, yeah, pretty fast glimpse and overview on it. But to get the instant rate of change, it's this formula. Limit as h approaches 0 of f of a. Oh yeah, f of x plus a. Why? The thing is, I was thinking about either put it in the formula that I had described. I put a, but in this instance it's x. It's the same thing. F of x plus h minus f of x over h. Right here, you see the thing we're trying to do here is mostly trying to factor out the h and cancel the denominator. So that's what we're going to try to do right now. Obviously, like in previous limit problems, we're just going to substitute the 0 into this. And that's where we get the slope. So that's what we're going to do right now. The function we were given is x minus 2 squared. Keep that squared in mind. So this is what we're going to do. Gavin told me to tell you to die. I'm just trying to educate people, man. Look. You see, this is why Gavin's failing my class. He should have come to tutoring, but no. Anyhow, let me continue with limits. Skylar. No. Malton, you got detention. Anyhow, let me continue with the class for those who are interested. Gavin gets detention too. Okay, yes. So like I was saying, this is the definition. I already took calculus. Don't worry. I'm not failing anything. Okay, yeah, okay, buddy. Okay. Congrats. But have you practiced your L'Hopital? Gavin says you're a bum. Why is everyone jumping on me, bruh? Why are y'all trying to jump me? I'm just trying to teach class. Okay. Look. We're gonna solve the tangent line, and then I'm gonna use it to bonk y'all in the head. Okay, so let's evaluate this. So first we gotta know what f of 2 is to actually find the tangent line. Gavin says hi. Hi. Look, don't forget how to factor x. Don't forget how to factor x squared minus 4. What are you talking about? Oh, yeah. Yeah, okay, I know what you're talking about. Yeah, I made a oopsie. Right, let's retract my step. Hold up. I know exactly what you're talking about. Yeah, I was thinking about that too. I was like, wait, this thing looks off. Wait, hold up. I know exactly what you're talking about. Let's go back here. Yeah, there's this problem. This is supposed to be a 4. Yeah, differences of squares doesn't work like that. Yeah. I get you. You know, because I was looking at this and I was thinking the same thing. I was like, what the? Huh. I made some of these problems like really late yesterday. I don't know. Oh yeah, I goofed up. I admit that. Anyhow, where is this? Where is the tangent line? Tangent line? No, that's in discontinuity. It's right here. All right. All right. So, first we gotta find f of 2. So in this case scenario, we don't have to do much. F of 2 is just gonna, look, the point is defined, right? But f of 2, well, f of 2 right here is gonna be 2 minus 1, which is just 1. 2 minus 1, 1 squared is 1. This is gonna be f of 2. We plug it into the function. It's gonna be f of 2 plus h squared. Oh, yeah, f of 2 plus h squared minus f of 2 over h. Should be like this. Someone could fact check me if you want. So yeah, we do that. And then we just evaluate. So oh sorry, limit sign. The limit sign. So right here we got 2 plus h squared, which oh wait, hold up. How could I forget? We got a minus 1 over here. Silly me. We have the minus 1. I forgot to add the minus 1. Oopsie. Yeah. Minus 1. So then we got 2 plus h minus 1 minus f of 2. And f of 2 in this case is 1 all over h. I might need to clear this to make more space, but for now we're gonna go to the bottom. I'm not writing the limits notation, just to conserve space, but we should be writing it. All right. I'm not writing this thing just to conserve more space, but we should be writing it. So continuing, right. We just distribute over here. Now there are easier formulas to do this, but I don't memorize that shit. I just do. Everything is multiplied at least 1. Yeah. You got like 4 plus 2h minus 2 should cancel out. And then we get plus, wait, what? Yeah, plus 2h plus h squared minus h minus h. Wait, what? Yeah, minus h minus 2h plus 1. And then there's this minus 1 right here, so we're just gonna add that right here. All over h. Now we could try and factor shit out. I mean, cancel stuff out. So we have a 2h. Hey, that's, something's off. I think something's off. Wait. Plus 4, 2h minus 2. No. I think that's right. Yeah. Plus 2h. Yeah, no, that's right. Okay. So right now we get, what? This is 4. So these cancel. This cancels with this. We leave a 2h. Get another 2h. And then these cancel with that. And then we get minus. This is minus. Oh no, positive 2. Yeah, we get positive 2. So at the end of the day, we get h squared plus 2. H squared plus 2 over h. We have that. Wait, let me clear this. Actually, yeah, we get this from all of that, I believe. Again, someone could always fact check me. We get all of that, and then we simply cancel this out. Yep, we cancel that out, and we're left with, we cancel all that out. Let me just delete that. So we get this. Hold up, I don't remember. Oh yeah, it was positive 2. Plus 2 over h. We cancel these out using the properties of, well, it's the properties of the exponents, but right, you know, we're gonna subtract the exponents. So this one has, let's say this one has an exponent of 1, we subtract the exponents, we get h. Limit as h approaches 0 of h plus 2. Yes, sir. And then we simply plug 0, like we did for all other limits. And then limit as h approaches 0 of whatever the gobbledygook we just did was equals 2. I'm not writing all that. I'm not gonna lie. But yeah, this is the instantaneous rate of change. You know, the thing we were talking about like 30 minutes ago? Yeah, that. And guess what? That's only one part of the problem. We still have to do so much more. And that's calculus for you. There's a lot. There's a lot. Nah, I'm kidding. Now, in this problem, there's only one more step, and it's like pretty basic, pretty easy. I'm pretty sure you go over this in algebra or geometry. Well, at one point, you go over this like really early on in your math career. So if y'all don't know it, you should. But hey, I guess y'all learn right now. So there's this formula known as point slope form. And that's y2 minus y1 equals m times x2 minus x1. Now, we've been given a point already. That's 2, 4. And we're trying to find the tangent line that corresponds to this point. So since we are already given y1, the initial value is going to be this, right? y1 is going to be 4, and x1 is going to be 2. We already have the instant rate, and that's going to be our m. So all we have to do is plug stuff in. So it's going to be y2 minus 4 equals 2 times x2 minus 2. And that right there is your tangent line. If you want a more precise answer, you just factor everything out and move the 4 to the right hand side. We could do that, but it's not necessary because we're gonna give out the same thing. But we could do that. I know in like AP classes or whatever, they don't need you to do that. If you're taking like AP Calc or something, they don't make you do this. But if you're taking any other types of calc, like I don't know, college calc or something, they make you do this. They don't give a fuck. they want the work, bro. So here we go. We do it. So let's just erase this, right? Pretend that y2 doesn't exist. We just move stuff out. It's gonna be, you factor this out. 2x minus, look, 2x and minus 2. That's minus 4. So it's plus 8. Oh wait, no, minus 8. Not bad. Wait, what? No, it's just 2x. There we go. Yeah, this would be your tangent line. It's y equals 2x. It wouldn't be nothing else because if you factor this out, 4 and then negative positive cancel out. So yeah, this would be your tangent line right here. The second part isn't hard. It's the first part that requires a lot of tedious work, and which is why I only did one example of this. I'm not doing another one. They're kind of fun to do. I'm not gonna lie. These were like one of my favorite things to like learn when I did it back in my day. But it's a lot of work, man. Especially when you get more complicated ones. Like whenever you get a square root one. God damn, that's so much work. But man, not as much work as when you start doing integrals. Or series. Series are yeah, nah. Anyhow. Enough about that. Y'all don't have to worry about that. Not in my class, at least. We're only doing limits, right? Y'all have to worry about limits when you take your quiz, if there's a quiz. I don't think there will be a quiz because I don't feel like grading anything. Anyhow, let me just continue. Let me continue with my thingamabobby. I just realized I never bothered putting the music back on. I had music playing for like a good segment of the stream, and they just went away after I heard like an ad start playing randomly. I don't know why. Oh no, I lost Twitch chat. Wait, hold up, guys. Let me bring it back up. Oopsie, that's okay. There we go. Just in case. I don't want to be like that one guy who. I've seen a clip of this guy who had like Kai Cenat in his chat. Never paid attention to the chat on Twitch. Bro fumbled. So I'm not doing that. I always read YouTube chat. I have Twitch open. I just barely read Twitch chat though, because I don't know why. More people like to use YouTube, so I use YouTube. But yeah, okay. Back to the math. Next slide. There we go. Okay. Oh, infinity. I think we're gonna be getting close towards the end of our lesson here. But yes, infinity. We can evaluate limits at infinity to determine end behavior, or just behavior at a certain point. It really depends. But typically speaking, for like normal functions, more. I don't know. I guess like better it for the eyes and the brain type functions. We're just gonna be using it for end behavior. But for one of these, like 1 over x, no. It's at a point. There's certain things that I put here that you should know, or things to note. You know, some trig definitions like tan of x, cotangent of x. The indeterminate forms. There's many forms that are indeterminate. Obviously, it's anything over 0. Infinity plus infinity. Or infinity minus infinity. That's I'm not gonna lie, I got a problem on that once, and it wasn't that great, because you know, some big number minus some big number should be nothing, right? But no, that's just indeterminate. Or some big number plus some big number should be some really big number, but no, that's indeterminate. Some big number divided by some big number makes no sense. There's nothing divided by nothing also makes no sense, so that's why it's indeterminate. Oh yes, and the trig limits. Limit as x approaches infinity equals 0. Don't know why. There's proofs for it, but it requires a lot of work, harder math. So we're not going over that, especially for the limit of sine of x over x. Because the only way to prove that is with a series. There's also like the ways to prove it with like triangles and shit, but no, we're not doing that. We're not doing that. I forgot. I should have done a problem on that. Damn. Hold on, trig limit. Oh, I think I have one, but I did it for infinity, and I might have messed up because I was thinking about doing it for as x approaches 0, but instead I did it for infinity. And when you do that, it usually doesn't end up working out, because like some certain like trig functions, they have their ranges defined already, and their ranges and domain already defined, so sometimes it doesn't work out that great. But let's just do these basic ones. So, oh my god, bro, imagine this is 4. Pretend this is 4, all right? So let's say we have x squared minus 4 over x plus 2, and we were to evaluate the limit. Now going off on past experience with like previous limit problems, we would simply just substitute the infinity sign into the instances of x. But you see, if you recall from the last slide, infinity over infinity simply is indeterminate, or it's just not doable. So there is a way of evaluating this, as we did in the previous example, and that's factoring. So limit as x approaches infinity of x squared minus 4 of over x plus 2. We simply factor using differences of squares again. And then we substitute the infinity sign into it. So we already have x minus 2, x minus limit as x approaches. Oh man, my tablet likes to goof up sometimes. I don't know why. It's in like this specific region too. Even when I'm doing doodles and stuff. But yeah, right here, limit as x. That's a really weird limit. But the limit as x approaches infinity of x minus 2. And now would you believe it or not, but some really huge number minus some small, really arbitrary number is not gonna do much. So if we were to substitute infinity here, the answer would still be infinity. So yeah, nothing much is gonna change. There's well, actually no. I was gonna say you could have also taken the ratios, but no, you can't do that here. I'll show you an example of what I'm talking about later. But when you have two, when you have a numerator and a denominator of the same powers, you could just take the ratios of their coefficients, and that would be the limit. In this case, it would just be, I think, 1. Yeah, it would just be 1. But in other cases, no. It's most notably this case, you can't do that. You have to factor. However, there's also cases where you simply just do some other little tricky thing. And that's you also take ratios in that, but in that case you factor out the x's of the highest term within the denominator. And we have examples on that, so I'll show you. I'll show you all right now, actually. Oh no, this is a tree limit. We're not doing this shit. No, pretend this is, I'll just do a normal limit as x approaches 0 because I didn't get to show y'all a trig limit in general. Look, as I noted in one of the slides, the limit of x approaches 0 of sine of x over x is just 1 by definition. Sorry guys, wait. By definition, it's just 1. That's it. That's the definition. It's just gonna be 1. There's many ways to prove it. All are tedious, all are very long, and some are complicated. So we are not gonna do that. But if you know trig, these should be light work. If you don't know trig, you should study up, especially before calc. Trust me, just trust me on it. Please save your life, save your soul. You're gonna struggle. You might not pass your final test. Trust me. Also learn your unit circle. That's which is this. You got your pi over. No, that's just pi, or pi 2 pi, pi over 6, pi over 4, pi over 3. I can't. That's pi over 2, and then you only really need to know this corner because everything else is just adding on. There's a way that I could do. I could probably make a video on it, but I don't know. It's not really that's not really the type of content I want to make. I'll just do educational stuff for streams, maybe some videos, but that's it. There's simple ways of doing that. We don't need to know that for this problem though, because we're just using 0. We're using 0. Unless, of course, we start substituting and we think that 0 is actually like talking about radians. And if it's in radians, then yes, we can evaluate it. Oh, wait, no, not 0. My bad. Theta. Ooh. Ooh. That would not be great. Okay. So, moving on. Let's actually evaluate it. Now we can't do this obviously because if we put a 0 in the denominator, it doesn't exist. All right, it doesn't exist. Indeterminate. So we have to factor. But how do we factor this? It's a trig function. The hell are we gonna do? Well, it's pretty simple actually. We know our trig definitions, or I hope you do. Tangent is the equivalent to sine over cosine. Cotangent, which is the inverse of tangent, is cosine over sine. Knowing this, we could simply rewrite this whole thing. All right. So the limit as x approaches, x approaches 0 will not be tan of 2x, but rather sine of 2x over cosine of 2x over x. And we could break this down even more by simply rewriting the fraction. Because if you think about it, sine of tangent is just being multiplied by 1 over x. It's the same thing. If you multiply a tangent by 1 over x, it's just going to go in the numerator in the, anyways. It's the same thing, so we could just do that. This is going to be sine of 2x or cosine of 2x times 1 over x. But wait, we can simplify even more. Look, you notice how right here in this formula, sine of x over x equals 1, right? So, by that logic, and since it's already being multiplied, the numerator is going to be multiplied anyways, right? Denominator is going to be multiplied. We could just move the sine of 2x across. It's the same thing, right? It's going to be the same thing anyways. So, we just move it. Sine of 2x, look, 1 over cosine of 2x times sine of 2x over x. And that we can evaluate with ease. All right? Look, cosine of 0, right? Cosine of 0. If we take a look at the unit circle, it's going to be like right here. This is going to be 1 comma 0, right? Yeah. This is 1 comma 0. This is the coordinates for when the angle is 0. When the angle is 0, these are the coordinates. 1 comma 0. All right? So, cosine is in regards to the x values of whatever coordinate lies on this circle. So, when we're referring to cosine of 0, it's going to be 1. No? Well, I say yes, because that's how it works. It's going to be 1. So, cosine of 1. Look, cosine of 0. We plug in, look, if we plug in 0, the 2 doesn't do anything, because remember, 2 times 0 is 0. So it's going to be 1 anyways, regardless of the 2 or whatever coefficients in front of the x. It's going to be 0. So moving this up here, just for simplicity, it's going to be 1 over 1 is 1, times sine of 2x over x. Now, think about it this way. If sine of x over x equals 1, and we have a 2 on the top, it's like saying 1 is being multiplied by 2 over 1. Or just 2. It's the same. It's literally the same thing. We could literally just say, this is 1 times 2. Oh, oops, I don't know how I deleted that. But yeah, that's 1 times 2. Alright? If we, it's the same thing. So at the end of the day, this really weird function, or in other words, this trig limit, turns into 1 over 1 times 2. 1 over 1 times 2, which is 2. What the heck is happening? What is this? What? Okay. I don't know. Yeah, so it's gonna be 2. So this limit equals 2. It just equals 2. It's really weird. It should equal 2, at least. I believe it equals 2. If you're evaluating 0. It should. But if I goofed up, that's fine. At least I showed y'all how to do like the basic trig process. Cause you're supposed to like, you're supposed to make these trig functions into more simplified versions. And then you'll be able to evaluate them easier. Unless you can, of course. If you can't do it, you can't do it. Alrighty then. Let's move on to the next topic. What is this? Oh, another limit. Well, it's not the next topic, sorry. We still have one more limit example to go. This is one of those cases that I had mentioned earlier, in which you have ratios, in which the numerator has a degree that's greater than the denominator, or vice versa. Now, these are polynomials, of course, except for the first one. That's quadratics. This is quadratic. This is a polynomial. For second degree, third degree, whatever. Anyhow, all you have to do for these is, well, you see, you're gonna get some infinity over infinity regardless if you use the substitution method. Because remember, some big, let's say you do this, you plug in infinity over here, it's gonna be some big number minus some really arbitrary number over some big number plus some really arbitrary number, and that's gonna be indefinite, an indefinite form. It's gonna be infinity over infinity. We can't have that, of course, and there are ways to simplify this, and that's by taking out the x's. Yes, so let me show you how to do that. For these types of problems, you take a look at the denominator and you divide everything. Well, you factor out the degree with the highest term. The my bad. The x with the highest term. So we get x cubed, right? Times, oh, well, wait. Times 4 plus 2. Now, what's 2x? 2x, if you factor out the x cubed, what is that? It really won't make sense, right? To factor out the x cubed, because you don't have an x cubed on the other one. But oh wait, remember, properties of exponents. You can write a fraction. Now, this might take me a minute, I'm not gonna lie. I could do this one though. I could do this one for sure. So look, let's say you had an x cubed right here. X cubed minus what would give you 2x, x squared. If you factor out remember, properties of exponents, like I was saying, x cubed over x squared equals x, because it's gonna be x. The 3 minus the 2 is gonna make an exponent of 1, meaning that you're gonna be only left with an x. So that's what we're trying to do right here. Use properties of exponents to factor out the x cubed. Same thing for here. This has no x term, so it's going to be 5 over x cubed. And then we have to do this process for all of the numerator. In fact, all of the terms in the numerator using x cubed as well. So it's 3 x cubed. 3 over x minus 2 over x squared minus 1 over x cubed. Ho ho. Would you look at that? Now, obviously these cancel out, and we're left with all of these terms right here. Now, what do we do when we have these? Example, we just evaluate the limit. We do the plug-in method with the substitution method. One thing that's important to note, 1 over x is always going to equal 0 when you're evaluating limits. Limit of 1 over infinity equals 0. That's something really important to know and something important to remember. All right? So for all of these terms, anytime there's an instance of some number over x, and you plug in the infinity sign, it's going to be equal to 0. So you're going to get 4 plus 0 over 0 minus 0 minus 0. Now, this isn't indeterminate because you have this 4 term over here, meaning that this whole limit is simply going to approach 0 of f of x. I'm not writing that. I hope my handwriting could use work, but let me just do this. Yeah, that's easier to understand. So since we have this 4 in the bottom, or more realistically speaking, it's gonna be this 0 over 4. 0 over 4. But yes, the limit would be 0. This whole thing is gonna approach 0. All right. So all you have to do is factor out the x's. The x with the highest term, the highest degree, I mean. In either the numerator or the, well, no, in the denominator, my bad. It has to be in the denominator. Can't be in the numerator. That's the rule. I don't make the rules. I just follow them. Oh, now we're getting into continuity. Oh, wait, but I didn't even show you. Nah, y'all can figure that one out. There's examples in which, no, wait, let me show you all the examples. Just, I wouldn't be a good teacher if I didn't show you. So, let's say, this was x cubed. Let's say that this was x cubed. You wouldn't have to do the factoring. Because just as we did in like the last example, you could do the factoring. You could do the factoring. Imagine you took the degree of the lowest term and of the highest term in the denominator. You did all that. Factor out the x cubed. Great. Well, these two have the same terms. So at the end of the day, when you factor out the x cubed, 3 and 4 are going to be left alone. These are going to all turn to 0. So what is that going to mean? Well, since you have 3 over 4, and these are finite values, the limit is going to, as x approaches infinity, is going to be equal to 3 over 4. It's simply the ratio between the leading coefficients. Yeah, the ratio of the leading coefficients. So when the degree is the same, and you're evaluating a limit at infinity, you can simply just take the ratio of the leading coefficients. And that, my friends, would be your answer. All right, now we're gonna get into like the final section of this whole little lesson. This whole lecture, actually. Lecture by Professor DJ. Yes, sir. Yes, sir. Man, I just noticed I have a lot of side jobs. I never thought I would be doing this. But here I am. Okay, so this is an important thing, obviously, like as is every other section of this whole segment, whole little lesson. But this kind of applies limits in a very simple way, a very beautiful way. This is continuity. And what is continuity? Continuity describes the behavior functions, well, at particular, well, not it just describes the behavior function, not at particular points. It just describes the behavior functions. It indicates whether a function exists or whether a function doesn't. Hey, Piro, welcome to the stream. Now, there are 3 rules to continuity, and they're as follows. Evaluated points of x must exist. All points on a set interval must exist. The limit of set x must also exist. And the output of an x value must be equal to the limit of the x value. So, just in case you didn't understand, let's say you had a line, right? Let's say on this line, this interval right here, each value here exists, right? Let's say you had a point right here. Since the limit of the right and the limit of the left, well, the limit of the left and the limit of the right coincide, right? That means, and this point right here exists. It definitely exists, right? That means that the function, at least on this interval, is continuous. And that's pretty much about it. It's much more easier to explain on a graph. But when you're trying to prove it with no graph, it gets a little complicated. Not really too complicated, but you'll get what I mean. I'll show y'all some examples. Oh, this is a graph of continuity, okay? Like I was saying earlier, left right here and the right here are approaching, okay, in the graph it says C. Let's say C is a defined point on this function. It's continuous. There are no jumps, no holes, and no asymptotes. The left and the right limits coincide on the given interval, meaning that the limit is continuous. Remember again, like I was saying earlier, a hole does not mean a limit doesn't exist, but it does mean that it's not continuous. That's it's a little tricky thing, but sometimes it is what it is. All right. Holes, unless it's like a different x value. Like let's say you were given a break right here, right? Imagine, ignore this part. We were given a break, but the question was asking you to prove that it was continuous over this interval. You wouldn't have to worry about any of this. No one cares about that. If a question was asking you only about this section, it wouldn't matter. But if it's everything or the whole function, then yes, it would matter. All right. So yeah, that's continuity, or at least the basic definition. Now we're gonna evaluate some other instances, which is discontinuous. This is continuous, right? So these are the main forms of discontinuity. There's we've already reviewed some of these, but at least in terms of limits. But some of these also like spread on to discontinuity. So right here, this is a jump discontinuity. It kind of looks like the function is jumping or breaking apart. Could be a jump or break discontinuity, same thing. It looks like the function is, you know, it's continuous up until this point, and boom, wham, just randomly decides to jump to another value, another y value, and then continues. Not cool, man. But it does it. And that's when it's discontinuous, a jump discontinuity. Remember that, because sometimes you get little easy questions in which they ask you to like identify types of continuity. And then might get it wrong if you don't remember the type. This is oscillation or oscillation. I don't know how to pronounce that. I'm not gonna lie. This is why I'm doing math, not reading. Remember, it goes like this. It's like a squiggly line, never approaching a finite value. It doesn't exist at the point x equals 0. It doesn't exist over here, like the center. Neither does the limit. So by definition, since neither the point nor the limits exist, the function as a whole is just discontinuous. It would be a little different if you were to evaluate the left and the right, the limits of like the left and the right of some other point, but at least at 0, no. The whole thing is continuous. And this right here on the my very right is unbounded behavior. Basically anytime there's an asymptote, there is some form of unbounded behavior. It's just showing you as a limit as x approaches infinity. That's what unbounded means. So all of the examples in which we looked at infinity have some type of unbounded behavior. Every function for that matter has some form of unbounded behavior, unless it's restricted in a certain interval. Like let's say you only wanted to, let's say it was a function of time. If it was a function of time of some specific thing, like okay, let's say we were playing FNAF. Let's say we were playing FNAF, and you know we started our shift at 6 a.m. and we started our shift at 12 a.m. all the way to 6 a.m. That means we would only be looking at that interval in time, not the rest of our days. We could have been like, I don't know, eating cereal at 5 p.m. if we wanted to. We wouldn't care because we're not looking at that. All right. So yeah, that's what unbounded behavior is. We're only looking at anything that happens afterwards. So right here, as it's only really present right here as x equals 0. It's right here at x equals 0. So yeah, this is where the unbounded part comes from. Also where y equals 1. Oh wait, no, y equals 0. My bad. Now when y equals 0, there's some form of unbounded behavior as well. But we're not looking at the y's when we're determining the Oh wait, we are. My bad. But that really depends on the type of limit you're evaluating, if it's the left-hand side or the right-hand side. Anyhow, this is a piecewise function, and we're gonna prove if it's continuous using the definition of continuity. Now, this is pretty easy to do. Like I said before, we just evaluate the left-hand limits and the right-hand limits, and as well, we have to also see if the points are defined. Now, by definition, when you have a less than or greater than symbol, it means that the point is defined. So we don't have to do anything about that. All right? We don't have to worry about that. The points are defined. To determine the left-hand side and the right-hand side, however, in a piecewise function, we have to use these inequalities right here. Now, there are breaking points. There are breaking points. But where, you might ask? Where are they, DJ? Well, they're at x equals 1 and x equals -2. How do I know that? Simple. Right here, right here, right here, right here. We're given those terms. Those are the breaking points. So those are the values in which it is possible for discontinuity to exist. So we have to evaluate everything at those points. Limits. Well, yeah, just limits, really, because we know the points exist. We just have to evaluate the limits. So, taking a look at the left-hand side of which one should we do? Should we do? Yeah, let's do 2. 2 from the left-hand side. The left-hand side would be referred to this one right here, where x is less than -2. So we would simply plug that in to 6x minus 4. By plugging that in, we don't have to do any we don't have to factor, do nothing, no simplifying. We get an easy term. That would just be like 3. Oh, oops. Sorry. Yeah, that would just be like that would just be -3. Oh, sorry. Ooh, my bad. That's -2, -2. That would be a fraction. Oopsie daisy. Wait. That would be -6 over 6, which would be equal to -1. That's that. So we'd get -1 for the left-hand side. That's -1. Keep that in mind. We're gonna keep writing them over here. Now I'm gonna actually leave this just prepared. Proof on the right. Now for the right-hand side, we take a look at this one right here, because this one determines, this one has a middle value. Plugging stuff in. 2 times 3, so there's negative, -5. That's 6 minus 5. That's -1. So right here, we see that the limits coincide, which means that the overall limit, the left-hand limit and the right-hand limit coincide. That means the overall limit, as x approaches 2, is -1 as well, which means it exists. Which also means it's continuous up until -2. It's continuous, all right? So far we're good. So far we're doing good, because we know that there's no break at -2, but there might be a break at -4. So, I mean, at 1. Oh boy, looking at this, if I'm gonna just deal with this thing, this is a monster right here. For this problem, we're gonna look at limit as x approaches 1 from the right. From the right, yes. 1 from the right. Evaluating it from the right, we notice we have a square root in the bottom. Now, I don't know about you guys, but the square root of 1 minus 1 is 0. And that's a no-no. So we have to do what we love and factor. Yay! But no, we're not factoring. We're rationalizing, which is even better. Okay, so x plus 1 over x minus 1. Simple. All we have to do, multiply the top and bottom by square root of x minus 1. Oh my, that's a minus. There we go. And that's how we rationalize, by the way, in case you don't remember. Then we distribute. So that would give us x square root x minus x plus square root x minus 1 over x minus, wait, what? X, yeah, no, x square root x minus x plus x plus square root x minus 1 over square root x, over x minus square root x plus plus square root x minus 1. There we go. Man, that seems easier. So these cancel out, and we can't cancel out anything over here. Oh man. So we're just left with this. X minus 1 or x square root x plus x minus, plus x plus square root x. What the heck? Minus 1. And then we just have to substitute and yada yada yada. That would get 1 plus 1. Okay, we get 1 plus 1 plus 1 minus 1, that's 3. Wait, 1 plus 1 plus 1 minus 1. Yeah, that's 2. Wait, what? Guys, I think I did something wrong. Hold up. Yeah, I did something wrong. Oh no. Owie. What did I do wrong? Yeah, I've done something wrong. Hold up. X minus 1 or square root x plus 1. Oh no! I wrote it wrong. I wrote the signs wrong. This is supposed to be a minus. Ooh. Ouch. We can rework that. Oops. Yeah, no. We can fix that. Easily. Easy peasy. Lemon squeezy. Yeah, no. Square root x. I know that top one shouldn't have a square root, but we're doing that for now. That's x. X minus 1 is going to stay there. Because square root x, let me just factor them out. I don't really want to, I don't want to stay too long doing this one. Okay, so square root x, that's x. X square root x plus minus 1. Yeah, it's like that. This would be square root, wait, no, it's x square root x plus x minus square root x minus 1. No, that would still, Ha! Oh wait, no, it cancels. There's one right here, x minus 1, yeah. You just, hold up, I just didn't see it. Yeah, that cancels. And then we got negative minus square root x minus 1. That's just 0. Oh, that's minus 2, I mean. Just negative 2. Hopefully that's negative 2. If not, I goofed up or something. I don't know. That should be negative 2, though. I'll check after stream. I'll check later, unless someone wants to fact check me. But hopefully we did good. Hopefully. Should be doing well. I don't know. But anyhow, so yes, that's the right hand side. If we take a look at the left hand side, it's pretty easy because we just have to plug stuff in, and that's gonna be 5 minus 3. 5 minus 3. That's 2. 5 minus 3 is 2. But look here, this one's negative, this one's positive. That means the limit doesn't exist, which means when x equals 1, the function isn't continuous. There's probably either like a hole or a break or some type of discontinuity. Oh wait, no, it is a break. It's a break. Yeah, there's no hole because the function is defined. So there's like a break. There's a jump. It's a jump discontinuity. It's continuous up to here, I believe so, and then it just randomly goes up to here. Imagine that. No, but I'm just saying this is an example. If we were to actually graph this, it would be like completely different. I'm not gonna lie. Which actually, I actually have a program ready for that. So if you give me 1 second, I'll graph it. I'll graph it right now. Hold up, I have Desmos up and ready just for this one reason. Hold up. Let me just x minus 1 over square root x minus 1. And then 5 minus 3x. I'm just graphing them real quick. 6 over x minus 4. So, hopefully this works. Oh, there we go. Yeah. So, oh wait, what the heck? Where did my arms go? There we go. Alright. So I'm looking at this graph right here. So it's gonna be from intervals negative, from intervals 1. We're looking at it from the interval of -2 to 1. -2 to 1. So it's gonna be like around here-ish. Yeah, there's a there's definitely a jump right here. Did I graph something wrong? X minus 1 over square root x minus 1. No? Yeah. Let's see. It's from -2 to 1. As we can see here, continuous all the way here. Right? Continue. This graph right here is continuous. So that would make sense, yes. However, this one, if we were evaluating it as x approaches 1, look, there's 1 right here at -2. This is the -2. And over here is the +2. Yeah, it's right here. So that explains that. And if we zoom out a little more, we see this is 1 over x type function. This is a line. This, of course, is the square root 1. All right. What is that? Yeah. So that's that. Nothing too bad. Nothing too bad. But yeah, I just wanted to show you that, because sometimes, you know, looking at a graph helps you understand it better. You know, sometimes it doesn't. That's okay. But anyhow, we solved that. And I'm not sure. Oh yes, we have. Oh oops, we have a few more slides left. So we proved discontinuity. Now there's these theorems. These are important theorems. The main 2 theorems of this whole section: intermediate value theorem and squeeze theorem. They just define like points. It's not too much. So intermediate value theorem just tells you that on a given interval, a point exists. That's pretty much it. So if a point is if an interval is defined, right, and it's continuous, there has to be a value in which some output equates to like some given input. Okay, so let's, in this instance, we put k. So if a function is continuous on a specific interval and k is any number between said interval, there's one x value in that interval where f of x equals k. Hopefully, y'all understand it. For some input, some given input, there has to be an output, no matter what, on an interval that's continuous. And a squeeze theorem is a little more complex. It's more for like evaluation of limits. So this one's more for like definition of like continuity. All right. So this one's continuity, and this one is limits. Yeah. So oh, I didn't prepare anything for this one because I thought I could just show it to you. So let's say you had a graph. This is a graph, right? And let's say this is 1 and this is 5, right? I think it could be safe to say that at some point in time, right, on this graph, let's say this is 1, and at 0.5, right here, it's 8. Let's say this is 1, 8, 1 comma, this is 1 comma 1, 5 comma 8, right? Basically, what an intermediate value theorem is saying is that at some point in time, right, it can be assumed, if the function is continuous, some x value had to have been like at least, I don't know, 5 at some point, right? It had to have at least been 5 at some point, because look, we made it to 8. We went from 1 to 8, and by that logic, we should have crossed 5 at some point. And that's what the intermediate value theorem is saying. There has to be, in a continuous function, a point at which a certain y value is reached when the x value lies on the interval given. All right. So I don't know what it would be, but there has to be a y value in which the x is 5. Wait, no, my bad. The x value in which the y value is 5. Yeah. That's what the intermediate value theorem is saying. More specifically in this example too. But in most examples, it's going to be like that. You could prove it in many ways. I'm not going to go into that right now. But that's pretty much the self-explanatory. Well, the theorem itself is kind of self-explanatory. But to prove it, a little tricky. But it's not too hard. All you really have to do is evaluate the limits of the endpoints. So you would have to, in this case, you have to take the limit as x approaches 1 and limit as x approaches 5 from the left to the right. No, from right, and then this one's to the left. And hopefully, at whatever point you're trying to evaluate, it equals the same thing. And yeah. Oh yes, let's move on to like the last section, today's lecture. Wait, hold up, just give me 1 minute. What is this? Is this? Oh yeah, squeeze theorem. I just prepared a little graph for you all. It's not hard, not too complicated. So, like I was saying, the squeeze theorem is talking about sandwiches. Well, the other name for the squeeze theorem is the sandwich theorem, and that's because it's kind of like sandwiches a function between two other functions, right? Now, essentially, this is used to evaluate limits, and here's how it works. You see, it could be safe to say, right, that at some point in time, they're gonna have an equal value. They're gonna intersect, all right? They're gonna intersect at some point in time. Just look at how close they are. They're being sandwiched. They're gonna be pressed together, compacted, like a bean burrito that a fat guy sat on or something. I don't know. It's gonna be compacted. Now, throughout this point in time, it's safe to say that at some point, and as long as these functions are continuous, of course, that the limit should be the same. So the limit of f of x, this one, or like the one, and h of x should be the same at their intersecting point, right? Because they're being sandwiched. And that's what is going to be happening, or how we're going to be evaluating them. So we're going to use the squeeze theorem to evaluate limit as t approaches 0 of t squared sine t 1 over t equals 0. Now And this is done in many ways, right? Sometimes you're already given a function in like this format, and like the less than equal than format. But when you have something like this that's a little harder, trickier to do, you would just use squeeze theorem, right? So how do we do this? Well, we know sine is a trig function, right? We know that. And the ranges of sine and cosine is from -1 to 1, right? That's the range. So we set up an inequality. -1 less than or equal to sine of 1 over t less than or equal to 1. And that's it. That's all. I'm kidding. No, that's not it, guys. Afterwards, you notice how we have a t squared, right? We're not, obviously, since we're talking about trig functions, that t squared isn't in a trig function. The 1 over t is an exception because it would be like the equivalent to sine of x. This is x, right? It's the same thing. But the t squared, it's a coefficient, some separate term being multiplied to sine. So how do we do that? Well, it's simple. To regulate this and add the t squared back, we just have to multiply the whole thing by t squared, right? Doing that would give us negative t squared less than or equal to t squared sine 1 over t and less than or equal to t squared, because this was positive, this was negative, right? And then we just have to take the limit of the end points, so the negative of t squared and t squared, and that would give us the limit of the middle. So doing that, since we're substituting t squared 0 into t squared, it's just going to be 0 and 0, right? Because look, t squared negative t squared less than or equal to t squared sine 1 over t less than or equal to t squared, simply 0 less than or equal to sine 1 over t. Wait, yeah, that, whatever. Less than or equal to 0. Yeah, the t squared. Is that's it. So that means that the limit as x approaches this value has to equal 0. And that's the whole point of the squeeze theorem. There are many other ways, many other examples. Y'all could search them up yourselves. But this is essentially the point of the squeeze theorem. It's just a way of evaluating limits that are a little tricky. But that's the whole point. That's literally the whole point. And it's beautiful. It's beautiful. It really is. Because it makes life easier. Especially for math. Alright. I'm not too sure, but I think, yeah, that concludes pretty much everything about limit and continuity. I'm not sure how I managed to do it, but I think I covered pretty much everything that Calc 1 has to offer in terms of limits. Yeah, that's limits, literally. I think I literally covered it all, bro. I did a pretty good job. What, I crammed it all into like, what, a little over an hour? But yeah, that's pretty much it for in terms of limits. I mean, well, continuity as a whole. There are many other examples out there online. If y'all want to practice, y'all could do that. But I tried my best to introduce like the concepts in like a small stream. I mean, it's my first time doing this shit. I think I did pretty good. I'm a little knowledgeable on the stuff. So yeah, you know, sometimes I goof up in terms of like adding and shit, but I know my stuff. I know my stuff. All right. I think I'm a good qualified professor. If you ask me. I do say so myself. But yeah, that's pretty much it for well, today's lecture. Hope y'all enjoyed. Hope y'all learned. And I don't know what we're gonna do for next stream, but if we do another education video, education stream like this one, I don't know. We'll do some hard stuff, some trickier stuff, and who knows? Maybe we might get a guest, so they could be bamboozled about all the wacky stuff I'm spitting out, all the wacky stuff I'm teaching you guys. But yeah, that's it for now, and I guess, well, class dismissed. Have a good one. Hey, I'll see y'all next stream. Hey, bye. Y'all could leave now. I mean, like, come on. Remember, you know that saying, the bell doesn't dismiss you, I do. Well, I don't really care about that. Y'all could just leave. I want to eat Fritos. I want to go to sleep. I got Marvel Rivals to play. I got to plan Sigma Month 3. Why did we skip from Sigma Month 1 to 3? Because Sigma Month 2 was lame. We had so much stuff planned for Sigma Month 2. Wait, I didn't even tell anyone that there was supposed to be more than one Sigma. Oh, fuck. That's the wrong place, bro. Bro, get out. Leave the school. Just leave, man. Why are you at the hallway?